related to first law of thermodynamics, some special forms of first law of thermodynamics, exact and inexact differentials, concept of enthalpy and relationship between delta H and delta E. In continuation, today we are going to discuss molar heat capacities, molar heat capacity at constant volume, molar heat capacity at constant pressure, Joule-Thomson effect, Joule-Thomson's coefficient and inversion temperature. First we will define molar heat capacity. By the term heat capacity, we mean the capacity to absorb heat and to raise the internal energy. When a substance absorbs heat, its temperature rises because the substance goes into the kinetic motion of atoms and molecules. Because of this, kinetic energy increases and increased kinetic energy increases the temperature. If Q calories of the heat is absorbed by the substance and temperature is changed from T1 to T2, then the heat capacity of the substance is given by the symbol C, and C is equal to Q upon M multiplied by delta T, which is equal to T2 minus T1. Thus, the heat capacity of a system is the heat required to raise the temperature of 1 gram of the substance through 1 degree Celsius or 1 Kelvin. If the substance is taken 1 mole, then M can be replaced by 1 mole and heat capacity will be equal to C equal to Q upon T2 minus T1. Here C represents molar heat capacity of the substance. Molar heat capacity of the substance can be defined as the heat required to raise the temperature of 1 mole of the substance through 1 degree Celsius or 1 Kelvin. Since the heat capacity varies with temperature, hence its true value is given by the expression C equal to dQ by dt. Here dQ is the small amount of heat absorbed and dt is the small change in temperature in degree Celsius or Kelvin. Hence, it can be said that molar heat capacity is defined as the ratio of heat absorbed to that of temperature change in Kelvin or degree Celsius. The average specific heat of water is 1 calories per gram per Kelvin, which is also equal to 4.184 kilojoule per kg per Kelvin, and the deviations of this specific heat are less than 1% in the range of freezing point to boiling point. The molar heat capacity of water will be equal to 18 calories per mole per Kelvin. Molar heat capacity will have the units calories per mole per Kelvin or joules per mole per Kelvin. Joules per mole per Kelvin is the SI unit of molar heat capacity. Heat is not a state function and neither is the heat capacity. Hence, it is required to give the procedure by which the particular state has been achieved. With the help of an example, we will calculate the heat required to raise the temperature of the substance. Calculate the amount of heat necessary to raise 213.5 grams of water from 25 degrees Celsius to 100 degrees Celsius. Molar heat capacity of water is 18 calories per mole per Kelvin. By definition, we know that C, that is molar heat capacity, is equal to Q upon T2 minus T1, or we can say that Q is equal to C multiplied by T2 minus T1 for 1 mole of the substance, but if there are n moles of the substance, then Q will be equal to n multiplied by C into T2 minus T1. Here, number of moles of water are 213.5 divided by 18 because 18 is the molar mass. Now, putting these values in the equation, we will have Q equal to 213.5 divided by 18 multiplied by 18 Here 18 is the specific heat of water multiplied by 373 minus 298. Q will come out to be 16.012 kilocalories. The two important types of molar heat capacities are molar heat capacity at constant volume and molar heat capacity at constant pressure. First, we are going to discuss molar heat capacity at constant volume. According to first law of thermodynamics, we know that dQ is equal to dE plus PdV. Differentiating this equation with respect to T, we will get dQ by dt equal to dE plus PdV divided by dt. At constant volume, dV will be equal to 0, hence putting the value of dV equal to 0, we will get dQ by dt equal to dE by dt at constant volume. As dQ by dt is equal to molar heat capacity, therefore, molar heat capacity at constant volume will be equal to dE divided by dt at constant volume. Thus, the molar heat capacity at constant volume may be defined as the ratio of change in internal energy to that of change in temperature at constant volume. Now, we will discuss the molar heat capacity at constant pressure. We know that C equal to dE by dt plus PdV by dt. We also know that enthalpy is equal to internal energy plus PV, that is H is equal to E plus PV. Differentiating this equation with respect to T, we will get dH by dt at constant pressure, which is equal to dE by dt at constant pressure plus dPV by dt at constant pressure. But dP at constant pressure will be equal to 0. Therefore, we will get dH by dt at constant pressure equal to dE by dt at constant pressure plus PdV by dt at constant pressure. Now, comparing this equation with equation number 5, we will get Cp equal to dH by dt at constant pressure. Hence, it can be said that the molar heat capacity at constant pressure is defined as the ratio of change in enthalpy to that of change in temperature at constant pressure. Now, we will relate Cp and Cv, that is molar heat capacity and constant pressure and molar heat capacity at constant volume. By definitions, it is clear that the two heat capacities, that is Cp and Cv, are not equal. Cp is greater than Cv by a factor which is equal to work done. At constant pressure, one part of the heat absorbed is used in increasing the internal energy of the system and the other part of the heat absorbed is used in doing the work of expansion. But at constant volume, all of the heat absorbed is used in increasing the internal energy, that is the temperature of the system, because no work is done. Hence, at constant pressure, the increase in temperature is lesser than the increase in temperature at constant volume. Therefore, Cp is greater than Cv by a factor which is equal to work done. We know that Cp is equal to dH by dt and Cv is equal to dE by dt. By definition of enthalpy, we also know that H is equal to E plus PV. For 1 mole of ideal gas, PV is equal to RT, hence replacing PV by RT, we will get H is equal to E plus RT. Differentiating this equation with respect to T, we will get dH by dt equal to dE by dt plus R. As dH by dt is equal to Cp and dE by dt is equal to Cv. Putting these values in this equation, we will get Cp equal to Cv plus R, or we can say Cp minus Cv is equal to R. Thus, Cp is greater than Cv by a factor R. This R is gas constant and its value is 1.987 calories per Kelvin per mole or 8.314 joules per Kelvin per mole. We can relate Cp and Cv and we can discuss an example related to this. 5 moles of oxygen are heated at constant volume from 10 degrees Celsius to 20 degrees Celsius. What will be the change in the internal energy of the gas? The molar heat of oxygen at constant pressure is Cp equal to 7.03 calories per mole per degree and R is given to be 8.31 joules per mole per degree. R is equal to 8.31 joule per degree per mole. As Cp is given in the units of calorie, hence we will convert R in the units of calories. To convert R in the units of calories, we will divide it by 4.184. So, R will be equal to 8.31 divided by 4.18 calories per mole per degree, which is equal to 1.99 calories per mole per degree. We know that Cp minus Cv is equal to R or Cv equal to Cp minus R. Here Cp is 7.03 and R is 1.99 in the units of calories. Therefore, Cv will be equal to 5.04 calories per mole per degrees. Heat absorbed by 5 mole of oxygen in heating from 10 degrees Celsius to 20 degrees Celsius will be equal to 5 into Cv into delta T, because Q is equal to n Cv delta T for n moles of the substance. Therefore, it will be equal to 5 into 5.04 multiplied by 10, which is equal to 252 calories. As the gas is heated at constant volume, so no external work is done. Therefore, W will be equal to 0. So, change in internal energy will be equal to heat absorbed, because we know that delta E is equal to Q plus W. Here W is equal to 0, therefore, delta E will be equal to Q. Putting the value of Q here, we will get delta E equal to 252 calories. Ratio of Cp by Cv is denoted by gamma and it is known as Poissons ratio. This ratio depends upon the atomicity of the gas. You can have a look on this table for the different values of Cp and Cv for monoatomic, diatomic and polyatomic gases. If the atomicity of the gas is 1, that is, gas is monoatomic, for example, helium, neon or argon, Cv will be equal to 3 by 2R and Cp will be equal to 5 by 2R. Hence, gamma, that is Cp by Cv, will be equal to 5 by 2R upon 3 by 2R, which is equal to 1.66. For diatomic gases, that is O2, N2, H2, Cl2, etc., Cv will be equal to 5 by 2R, Cp will be equal to 7 by 2R and gamma, that is Cp by Cv, will be equal to 7 by 2R divided by 5 by 2R, which is equal to 1.4. For triatomic or polyatomic gases like CO2, NO2, etc., Cv will be equal to 3R, Cp will be equal to 4R and gamma, that is Poissons ratio, which is equal to Cp by Cv, will be equal to 4R divided by 3R equal to 1.33. You can note that as atomicity of the gas increases, the value of Poissons ratio, that is Cp by Cv, decreases. If there is a mixture of the gases, we can calculate the molar specific heat of the mixture. Let N1 and N2 moles of two non-reacting gases A and B are mixed, then heat capacity of the mixture may be calculated as Cv, that is heat capacity of the mixture, will be equal to N1 Cv1 plus N2 Cv2 divided by N1 plus N2. We can calculate delta E and delta H in terms of Cv and Cp. First, we are discussing delta E. For 1 mole of an ideal gas, we have the relationship Cv equal to dE divided by dt, or we can say that dE is equal to Cv multiplied by dt. For a finite change, we will have delta E is equal to E2 minus E1, which is equal to Cv multiplied by T2 minus T1. For n moles of an ideal gas, we will get delta E equal to E2 minus E1, which is equal to n multiplied by Cv multiplied by T2 minus T1. For delta H, we know that delta H is equal to delta E plus PV. Hence, delta H will be equal to delta E plus delta PV. For 1 mole of the gas, PV is equal to RT. So, putting the value of PV equal to RT, we will get delta H equal to delta E plus delta RT. As R is a constant, this equation can be written as delta H equal to delta E plus R delta T. As delta E is equal to Cv into T2 minus T1, therefore, we can say that delta H is equal to Cv T2 minus T1 plus R T2 minus T1. Taking T2 minus T1 common, we will get Cv plus R multiplied by T2 minus T1. We know that Cp minus Cv is equal to R. Hence, putting the value of Cv plus R equal to Cp, we will get delta H equal to Cp multiplied by T2 minus T1. And for n moles of the ideal gas, we will get delta H equal to n Cp into T2 minus T1. We can correlate delta H and delta E with the help of an example. Calculate the value of delta E and delta H on heating 128 grams of oxygen from 0 degree Celsius to 100 degree Celsius. Cv and Cp on an average are 5 and 7 calories per mole per degree. You know that delta E is equal to n into Cv into delta T, which is equal to n into Cv into T2 minus T1, and delta H is equal to n into Cp into T2 minus T1. Number of moles has to be calculated as weight of the gas divided by molecular mass of the gas. Therefore, n will be equal to 128 upon 32 equal to 4 moles. Here T2 is 100 degree Celsius, which is 373 Kelvin, and T1 is 0 degree Celsius, which is 273 Kelvin. On substituting these values, we will get delta E equal to 4 into 5.0 into 373 minus 273, which is equal to 4 into 5 into 100 equal to 2000 calories or 2 kilocalories. On substituting the values in the expression for delta H, we will get delta H equal to 4 into 7 into 373 minus 273, which is equal to 4 into 7 into 100 equal to 2800 calories or 2.8 kilocalories. There is another example to practice the relationship between delta H and delta E. 3 moles of an ideal gas with Cv equal to 5 calories per degree per mole at 10 atmospheres and 0 degrees are converted to 2 atmospheres and 50 degrees. Find delta E and delta H for the change. R is given that 2 calories per mole per degree. As we know that delta E is equal to n Cv dt, therefore, putting the values, we will get delta E equal to 3 multiplied by 5 multiplied by 323 minus 273, which is equal to 750 calories. As delta H is equal to n Cp dt, or we can say Cp is equal to Cv plus R. So, putting the value of Cp, we will have delta H equal to n Cv plus R multiplied by dt. Putting all the values, we will get 3 multiplied by 5 plus 2 multiplied by 323 minus 273, which is equal to 1050 calories. Now, we will discuss an important effect of thermodynamics known as Joule-Thomson's effect. Joule and Thomson showed that when a gas at high pressure is allowed to expand in a region of low pressure adiabatically, appreciable cooling appears. The phenomena of producing lowering of temperature when a gas is allowed to expand adiabatically from a region of high pressure to a region of low pressure is known as Joule-Thomson effect or Joule-Kelvin effect. The apparatus used by Joule and Thomson to measure the temperature changes when a gas expands from a region of high pressure to a region of low pressure is shown here in this figure. An insulated tube is fitted with a porous plug in the middle and two frictionless pistons A and B on the sides. Let a volume V1 of the gas at pressure P1 be forced through the porous plug by a slow movement of piston A. The gas in the right hand chamber is allowed to expand to volume V2 and pressure P2 by moving the piston B outwards. The change in temperature is found by taking the readings on the two thermometers. Most of the gases were found to undergo cooling on expansion through a porous plug in adiabatic conditions. But hydrogen and helium were exceptions, as they showed a warming effect instead of cooling. The work done on the gas at the piston A in the figure is P1 V1 and the work done on the gas at the piston B is P2 V2. Hence, the net work done by the gas is P2 V2 minus P1 V1. As we know from the first law of thermodynamics that delta E is equal to Q plus W. But Joule-Thomson experiment is done in adiabatic conditions, hence Q will be equal to 0. Putting the value of W in this equation, we will get delta E equal to E2 minus E1 equal to W, which will be equal to minus P2 V2 minus P1 V1. Here the sign of W has been changed because it is the work done by the piston, or E2 minus E1 will be equal to minus P2 V2 minus P1 V1. On rearranging this equation, we will get E2 plus P2 V2, which is equal to E1 plus P1 V1. As E2 plus P2 V2 will be equal to H2 and E1 plus P1 V1 will be equal to H1, we will get H2 equal to H1, or we can say that delta H equal to 0. Thus, the process of Joule-Thomson's experiment takes place at constant enthalpy. In Joule-Thomson's experiment, when a gas expands adiabatically from a region of high pressure to a region of low pressure through the porous plug, the temperature change produced per atmosphere drop in pressure under constant enthalpy conditions is called Joule-Thomson's coefficient. It is represented by the symbol mu. Mu is denoted as dt by dp. If Joule-Thomson's coefficient is positive, gas cools on expansion, but if Joule-Thomson's coefficient is negative, gas warms on expansion in Joule-Thomson's experiment. The temperature at which sign changes is called inversion temperature. Most of the gases has positive Joule-Thomson's coefficient, hence they cool in Joule-Thomson's experiment. Therefore, if the Joule-Thomson experiment is done in series, the gases can be liquefied. The inversion temperature of hydrogen is minus 80 degrees Celsius. Above the inversion temperature, Joule-Thomson's coefficient is negative. Thus, hydrogen warms up during the expansion in Joule-Thomson's experiment at room temperature. Therefore, hydrogen has to be cooled below minus 80 degrees Celsius first so that it can further be liquefied by Joule-Thomson's experiment, and same is the case with helium also. In today's lecture, we discussed molar heat capacities, molar heat capacity at constant volume, molar heat capacity at constant pressure, Joule-Thomson effect, Joule-Thomson's coefficient and inversion temperature. In continuation, in next lecture, we will derive an expression for inversion temperature and work done in reversible expansion of ideal gases.